Hello, welcome to Module 5 of second week of our course on Introduction to Dynamical Models in Biology. In last couple of lectures, we have discussed about direction field, steady state, stability of those steady states. If you remember, all the examples that we discussed there are involving just one single ODE. That means we have only one dependent variable which is changing with time. But for most of the real life problems in biology and others, actually the number of dependent variable is more than one. So if you remember the initial discussions on writing ODE based model, if I have more than one ODE, more than one dependent variable, for each dependent variable I have to write a ODE representing rate of change of that dependent variable with time. That means if I have two dependent variable, I will get 2 ODE. If I have 4 dependent variable, we will get 4 ODEs. These ODEs together will be called system of ODEs. So in this module today, we will try to understand the issue of stability for a system of ODE. And for a single ODE, we have done some direction field analysis. We will have an equivalent thing here, which we will call phase plane analysis. So let us start. So suppose, let us take a simple example. We are taking the example of predator-prey model. So in a predator-prey model, there are two dependent variables, the population size of the prey and the population size of the predator. One represented by x and the other one represented by y. So I have some generalized equation written here. dx dt is equal to, this is the first ODE, is equal to k1 into x into minus k2 xy. For a predator, the rate of change is dy dt is equal to k2 into x into y minus k3 into y. X and y here are dependent variable changing with time. K1, K2 and K3 are the parameters. Let us don't bother about the parameters right now. Now how do we define the steady state for this system? For a single ODE, we have defined steady state as like this. Steady state is the value of x, the dependent variable for which its derivative is 0. So if you give me a ODE, dx dt is a function of x and t, then I make dx dt equal to 0 and identify the value of x algebraically for which dx dt will be 0. For a system represented by more than one dependent variable, for example this predator-prey system, the steady state is a situation where both the derivative of both the dependent variable are 0. So if I go back to this predator-prey model, I have two dependent variable x and y. So I have two derivative dx dt and dy dt. So steady state is possible or achieved when dx dt is also 0 and dy dt is also 0. Both the derivatives are 0. So at steady state, derivatives of all the dependent variables are simultaneously 0. Now how can we calculate that algebraically? Let us try to see it. So we will take the same example. I have two ODE, dx dt equal to k1 into x minus k2 xy, dy dt is equal to k2 xy minus k3 y. As we have defined, at steady state, both the derivative has to be equal to 0. That means dx dt equal to 0 and dy dt equal to 0. So that means I can make this one equal to 0 and this one equal to 0. So let us make. So that means k1x minus k2xy would be equal to 0. And from the second ODE, using this concept idea of steady state, we can say k2xy minus k3y would be equal to 0. So this is my first equation, this is my second equation, and I have to solve them simultaneously to get the value of x and y for which these two equations are true. So let us try how to do that. So let us take the first equation, equation 1. k1x minus k2xy equal to 0. I can take x common. So I will get x into k1 minus k2y equal to 0. That means either x equal to 0 or k1 minus k2y equal to 0. Now if k1 minus k2y is equal to 0, I can separate out y on the left hand side and the rest on the other side, and I get this relation y equal to k1 by k2. That means from first equation I am getting either x equal to 0 or x equal to y equal to k1 by k2. Now we will put this value of x and y in the next equation to solve. So the next second equation is k2xy minus k3y equal to 0. So let us consider when x equal to 0. So if x equal to 0, this second equation becomes k2 into 0 into y minus k3y equal to 0. That means y is equal to 0. That means when x equal to 0, y have to be 0 to simultaneously make these two equations 1 and 2 correct. Let us take the other value we have got from the first equation when y equal to k1 by k2. So let us take the second equation and plug the value of y in that. So we get k2 into x into k1 by k2. This is nothing but y minus k3 into y, that is k1 by k2 is equal to 0. We have only x, so we separate out x, take x on the left hand side of the equation and rest of the thing, the constant, the parameter on the other side, and we get x equal to k3 by k2. So what we have got? We have two equations 1 and 2 which we obtained by making the derivative equal to 0 for both the dependent variable, and we have solved them simultaneously. So we got two solutions. One is x equal to 0, y equal to 0. The other one is x equal to k3 by k2 and y equal to k1 by k2. So that means the system has two steady state. The first steady state is x equal to 0, y equal to 0. You can easily see if you put this value of x equal to 0 and y equal to 0 in this original ODE, dx dt and dy dt both will be 0. And the other steady state that we have in this system is x equal to k3 by k2 and y equal to k1 by k2. You can also check it. Take the value of x here and put here and here in the first ODE and in the second ODE. Take the value of y and put the value of y here, the first ODE and in these two second ODE. You can use simple algebra and calculate and see that for this value of x and y, both dx dt and dy dt is equal to 0. So our system of this predator-prey has two steady states. Now let us try to understand this steady state or identify this steady state graphically. Remember, to understand the behavior of x, a dependent variable with respect to time, when we have only one dependent variable and one ODE, we have used direction field. Now in this case, we have two variables, x and y. So I cannot use the concept of direction field directly if I want to see the evolution of x and y both together. So we will use a different trick, different method. So to learn that, let us simplify our problem. We keep the same ODE for predator-prey model. Dx dt equal to k1x minus k2xy and dy dt is equal to k2xy minus k3y. To make our life simple, I have considered all the parameters k1, k2, k3 is equal to 1. That will make our calculation easy. You can take any other value. So now at steady state dx dt equal to 0. So that means x minus x into y is equal to 0. So that means I will get, if I take x common, so I get a relation x into 1 minus y equal to 0. So either x equal to 0 or y equal to 1. So I have two solutions to this equation. Now I want to represent it graphically. How should I do it? Remember, in case of one variable, I can always plot the dependent variable versus the independent variable, the time. In this case, we will do something else. We will plot y and x both the dependent variable in this two-dimensional space. So that's why I have plotted x in this horizontal axis, y in this vertical axis. So any point on this space xy plane is the value of x and y at that moment. As time will change, value of x and value of y will change as per the given ODEs, so we will get multiple points and these points will keep on moving. So what I have done here, I am trying to plot x and y both together as they change with time. We will try to see how they change with time and how the plot looks like, but let us come back to the initial basic issues of this plot. So this type of plot is called phase plane and phase plot. What is phase plane? I have two dependent variables x and y, one in the horizontal axis, the other in the vertical axis, and this plane x and y plane is called phase plane. And the plot that we will make here will be called phase plot. So look back to the steady state relation. At steady state dx dt is equal to 0. From that we have got x equal to 0 and y equal to 1. So let us plot this on this phase plane of x versus y plane. How would they look like? X equal to 0 is this vertical line. At all these value x is equal to 0, and this red horizontal line here is y equal to 1. Now let us do the same thing for the second ODE. As you remember, in steady state both the derivative has to be 0. So I put dy dt equal to 0. That means from the second ODE I get x into y minus y is equal to 0. The parameters k1, k2, k3 are 1. So my life is easy. So I get the relation x into y minus y is equal to 0. Now I can solve this. Obviously I can take y common. So I get y into x minus 1 equal to 0. So either y equal to 0 or x minus 1 is equal to 0. So that means x minus 1 is equal to 0. That means x equal to 1. So I have two solutions, x equal to 1 and y equal to 0. Just like the previous case, let me plot this x equal to 1 and y equal to 0 in this phase plane. The blue line I have drawn to represent these two lines. So the vertical blue line is x equal to 1, and the horizontal blue line along the axis is y equal to 0. So I have four lines, two red which we have got from dx dt equal to 0 and two blue which are from dy dt equal to 0. So as I have two lines, for red lines, both the red lines, dx dt is equal to 0. That means along this line, in this plane, x does not change with time. So for this red line and for this red line, dx dt is equal to 0. Here also, dx dt is equal to 0. So these two lines are called x null lines. Null means 0, clines means slope. So slope of x along these lines are 0. That's why this is called x null lines. Whereas for the blue lines, we have got this blue line using dy dt equal to 0. That means y is not changing with time. So for this blue line, dy dt is equal to 0, and for this blue line also, dy dt is equal to 0. So I have two y null lines. Again, these are null lines because null means none, not, and clines means the slope. So obviously it is called y null because the slope of y with respect to time is 0 along these lines. So I have 4 null lines. 2 x null line shown by red colored line, 2 y null line shown by blue colored line. Now let us see where x null line and y null line intersect. I have 2 points where these blue and red lines are intersecting. One is 1 1 shown by this yellow dot. Another one is this 0 0. Don't confuse with this intersection point of 2 red lines or 2 blue lines. They are intersection of the same type of null line. Intersection of red null lines are intersection of 2 x null line, and intersection of 2 blue lines are nothing but intersection of 2 y null lines. We are not interested in them. We are interested in intersection of x with y null line. So I have 2 such positions where a blue line representing the y null line is intersecting with a red line representing the x null line, and that are 1 1 and 0 0. And why I am interested in that? Because at this point both the null lines have slope 0. That means at this point, at this intersection point, dx dt is also 0, dy dt is also 0. As both these derivatives are 0, that means these are steady states for this system as we have defined earlier. So just plotting these null lines on the phase plane and looking for intersection point, we can identify how many steady states are there. So if I have 2 dependent variables, I can plot them in a phase plane, and then I can put each of their derivative is equal to 0 and draw the null lines, and I will try to look for the intersection point. It can happen that for a system there is no steady state, so the null lines does not intersect at all with each other. That means you have no steady state there. If these 2 null lines intersect only at one point, that means this system has only one steady state. If the null lines intersect at 2 points, as they have intersected in this example, that means the system has 2 steady states. Once we have identified the steady states, then we can ask the questions of stability of this steady state, and also ask how the system, the x and y value, will change with time or evolve with time around the steady state. We will discuss those in another module. So let us jot down the key points. For a system of ODEs where you have more than one dependent variable, at steady state, the derivatives of all the dependent variables are 0. We can identify this steady state by putting all the derivative equal to 0 and then solving those equations simultaneously. Using simple algebra, we can identify the steady state. We have also discussed about phase plane. In a phase plane, 2 axes represent 2 dependent variables, and actually we want to understand the time evolution of these 2 variables in this plane and want to see this in this plane. A phase plot is nothing but a graphical display of time evolution of 2 dependent variables in a phase plane. We have not drawn the phase plot yet. We have just introduced the concept here in this module. Now in a phase plane, if you draw all the lines or curve for which the derivative of a dependent variable is 0, those lines or curves will be called null lines. And as I have discussed, intersections of null lines of 2 dependent variables are the steady states of the system. That's all for today. Thank you for watching. See you in the next module.